Imagine building a house. You pour the foundation, frame the walls, run the wiring, install the plumbing. It takes months, maybe years. Now, imagine driving past that lot the morning after the concrete was poured and finding a finished mansion with furniture inside. That is what the James Webb Space Telescope found when it looked at the earliest moments of the universe. Galaxies that should have taken billions of years to assemble were already there, fully formed, chemically mature, in the first few 100 million years after the Big Bang. Objects so massive and so complex that no model of cosmic history can produce them in the time available. And this is not one measurement. It is hundreds of objects, across dozens of surveys, confirmed by independent teams, all saying the same thing. The timeline we built for the universe does not work. The factories were running before the building permits were issued. What you are about to see is 3 years of evidence from the most powerful telescope ever built, data from X-ray observatories and ground-based instruments spanning 11 billion years, and a mounting case that the standard model of cosmology is either missing something fundamental or wrong entirely. It started with a single photograph, taken from 1 million miles away, of a patch of sky no bigger than a grain of sand. On July 12, 2022, NASA released the first full-color images from the James Webb Space Telescope. The target was a patch of sky no bigger than a grain of sand held at arm's length, centered on galaxy cluster SMACS 0723. The image contained thousands of galaxies stretching back over 13 billion years. Within hours, astronomers around the world began downloading the raw data, and within days, some of them started finding objects that made no sense. JWST had been in development for 25 years. It cost roughly $10 billion. Its primary mirror spans 6.5 meters across, made of 18 hexagonal segments coated in a layer of gold thinner than a human hair. The entire assembly sits behind a sunshield the size of a tennis court, folded for launch and slowly unfurled over 2 weeks as the telescope drifted to its permanent home at Lagrange Point 2, a gravitational sweet spot about 930,000 miles from Earth, where it orbits in lockstep with our planet, always keeping its back to our star. The telescope launched on Christmas Day, 2021, aboard an Ariane 5 rocket from French Guiana. It arrived at L2 on January 24th. 6 months of calibration followed. Engineers aligned the 18 mirror segments to within a fraction of a wavelength of infrared light. The instruments came online, one by one. NIRC, for near-infrared imaging. NIRSpec, equipped with a micro-shutter array, capable of observing over 100 objects simultaneously. MIRI, for mid-infrared, each tuned to see light stretched by cosmic expansion from visible wavelengths into the infrared. The mission had a specific purpose. JWST was built to observe the first galaxies that formed after the Big Bang. Cosmologists had spent decades building models of what those galaxies should look like. Small, dim, simple clumps of hydrogen and helium gas, maybe 100 million times the mass of our star at most. These predictions came from Lambda CDM, the standard model of cosmology that has dominated the field for a quarter century. Lambda CDM describes a universe made of roughly 5% ordinary matter, 27% dark matter, and 68% dark energy. It predicts that galaxies assembled slowly, growing through hierarchical merging over billions of years, starting as tiny seeds and gradually combining into the massive structures we see today. The first deep field image was supposed to confirm this picture. Instead, the data contained bright, compact sources at distances corresponding to the first few 100 million years after the Big Bang. They were too bright. Preliminary photometric estimates suggested masses far exceeding anything the models allowed. Astronomers flagged them, ran the numbers again, and got the same results. At this stage, nobody panicked. New telescopes always produce surprises in their first data. Calibration uncertainties were large. The photometric redshifts could be wrong. The mass estimates relied on assumptions about stellar populations that might not hold at extreme distances. Every experienced observer knew the drill. Wait for spectroscopic confirmation before drawing conclusions. The anomalies were noted, flagged for follow-up, and filed as preliminary. But the follow-up data did not make the problem go away. Over the next several months, as more surveys came online and more fields were observed, the anomalies multiplied. They appeared in JADES, the deepest survey, in CEERS, in Cosmos Webb, the widest. Different teams using different instruments looking at different patches of sky kept finding the same thing. Objects in the early universe that were too massive, too bright, and too structured to exist under any version of the standard model. In February 2023, a team led by Evo Lab at Swinburne University in Australia published the paper that turned those scattered anomalies into a crisis. The Cosmic Evolution Early Release Science Survey, known as CEERS, had identified 6 galaxy candidates at high redshift. Each one appeared to exceed 10 billion solar masses. That is 10 billion times the mass of our star, packed into a galaxy that formed when the universe was barely 500 million years old. To understand why this was a problem, consider what 10 billion solar masses means. The Milky Way, our own galaxy, contains roughly 200 billion stars and has been assembling for over 13 billion years. These 6 candidates had apparently accumulated a significant fraction of that mass in less than 1/20th of the time. The analogy that circulated through astronomy departments was immediate and blunt. Finding these galaxies was like discovering a skyscraper in a neighborhood where the concrete foundation was poured yesterday. Lab's team used NIRC photometry to estimate the redshifts and stellar masses. The galaxies appeared at redshifts between roughly 7 and 11, corresponding to the first 300 to 700 million years after the Big Bang. At these epochs, the standard model predicted galaxies of maybe 100 million solar masses. The CEERS candidates were 10 to 100 times more massive than the upper limit of any prediction. Mike Boylan-Colchin, a theoretical astrophysicist at the University of Texas at Austin, took the CEERS results and pushed them further. His 2023 paper in Nature Astronomy, which framed itself as stress testing the Lambda CDM model, calculated something remarkable. If you took the mass estimates at face value, these 6 galaxies collectively contained more stellar mass than the total baryonic budget of the universe should have allowed at that epoch. The universe simply had not produced enough matter to fill them. It was as if someone had spent more money than existed. The paper landed hard. Headlines called them impossible galaxies. Cable news ran segments. Social media exploded with claims that the Big Bang had been disproven, which it had not. The actual situation was more specific and more interesting than the headlines suggested. The Big Bang itself was not in question. What was in question was everything that came after it. Lab's CEERS paper acknowledged the uncertainties. Photometric redshifts are estimates, not measurements. They rely on the brightness of an object across multiple filters to infer its distance. Without spectroscopy, which breaks light into its component wavelengths and identifies specific emission or absorption lines, the redshifts could be wrong. A galaxy that appears to be at redshift 10 might actually be at redshift 3, with its colors mimicking a more distant object due to dust or unusual stellar populations. The astronomy community responded the way it should have, with skepticism. The masses could not be right, critics argued. The instruments were new. The calibration was still being refined. Photometric redshifts at these distances had never been tested against spectroscopic confirmation because no telescope had ever been capable of providing that confirmation. JWST was, for the first time, operating in territory where there was no independent check. So, the community waited for spectroscopy, and when spectroscopy arrived, it told a story that was more complicated than either side expected. The spectroscopic follow-up began in late 2023 and continued through 2024. Teams using NearSpec targeted the CEERS candidates individually, breaking their light into spectra and searching for emission lines that would pin down their exact redshifts. The results came back mixed, and the story that emerged was messier than the original headlines. First, the critics were partially right. NearCam's calibration in its first year of operation had systematic offsets. The photometric pipeline overestimated fluxes at certain wavelengths, which inflated the inferred stellar masses. When the data was reprocessed with updated calibration, some of the mass estimates dropped, in certain cases, substantially. Second, some of the redshift estimates shifted. A few candidates turned out to be at lower redshifts than initially estimated, meaning they were closer and had more time to form. Others were confirmed at their original high redshifts, but with revised masses. The 6 galaxies that had launched 1,000 headlines were no longer all sitting at 10 billion solar masses. The media moved on. The corrections made for a less exciting story. Galaxies, slightly less massive than previously thought, does not generate clicks. The crisis, as far as most coverage was concerned, had been resolved. Science had self-corrected. Everything was fine. Everything was not fine. The revised masses were still too high. After every correction, after recalibration, after spectroscopic confirmation, the galaxies at high redshift remained significantly more massive than Lambda CDM could produce. The corrections had shaved the numbers down from impossible to merely inexplicable. Boyle and Kolchin's fundamental calculations still held. The early universe contained more stellar mass than the standard model's baryonic budget permitted at those epochs. In 2025, a team running the Renaissance simulations offered another avenue of reduction. They demonstrated that if the first generation of stars followed a top-heavy initial mass function, meaning a disproportionate number of massive stars formed compared to modern populations, the inferred masses from JWST photometry would drop by roughly a factor of 10. Massive stars are brighter per unit of mass, so fewer of them are needed to produce the same luminosity. This was a legitimate physical argument. If the earliest stellar populations were dominated by heavyweights, then what looked like 10 billion solar masses of ordinary stars might actually be 1 billion solar masses of very bright ones. A factor of 10 reduction sounds like it solves the problem. It does not. Even at 1 billion solar masses, these galaxies at redshifts above 10 exceed what hierarchical assembly models predict by a wide margin. The top-heavy initial mass function reduces the tension. It does not eliminate it. This pattern, where a correction reduces a crisis from dramatic to merely persistent, is worth paying attention to. It happens often in science. A dramatic claim generates attention. A correction follows. The public loses interest, but the underlying anomaly survives the correction. It sits quietly in the data, waiting for someone to explain it. The overcounting scandal, as some astronomers began calling it, did not prove the crisis was fake. It proved the crisis was real, but less photogenic than the first round of papers suggested. So the question shifted. If the galaxies are real, and their masses are genuinely higher than predicted, even after every reasonable correction, then something about how stars formed in the early universe was fundamentally different from anything the models assumed. The question was no longer whether JWST found something strange. The question was how the early universe managed to turn gas into stars with an efficiency that no known physics can explain. Star formation efficiency is one of those numbers that sits quietly at the foundation of astrophysics. It holds up a lot of weight without attracting much attention. It measures the percentage of available gas in a galaxy that actually converts into stars over a given period. In the modern universe, that number hovers around 10%. Roughly 90% of the gas in a typical galaxy never becomes a star at all. The reason for this low efficiency is well understood. Stars form inside dense clouds of molecular gas that collapse under their own gravity. But as soon as the first stars ignite, they fight back. Radiation pressure from hot young stars pushes surrounding gas outward. Stellar winds carve cavities in the cloud. When the most massive stars die as supernovae, the explosions blast remaining gas out of the region entirely. This feedback cycle limits how much gas any single episode of star formation can consume. Turbulence within the gas cloud adds another break, preventing large-scale coherent collapse. 10%. That has been the number everywhere astronomers have looked, across galaxies of different sizes, at different distances, in different environments. It appeared to be something close to a universal constant of galaxy physics. And then JWST found the blue monsters. Blue monsters are a class of galaxies identified in the CEERS and JADES surveys at redshifts above 10, corresponding to the first 400 million years after the Big Bang. They are tiny. Their radii measure between 100 and 400 parsecs, which translates to roughly 300 to 1300 light-years. For comparison, the Milky Way spans about 100,000 light-years. These galaxies are smaller than some individual nebulae in our own galaxy, but their ultraviolet output is extraordinary by any measure. Their UV spectral slopes, designated by the Greek letter beta, come in at -2.5 or steeper. This indicates stellar populations that are young and hot, almost entirely unobscured by dust. They are blue because they are furiously producing massive, short-lived stars that burn through their fuel in a few million years. The stellar masses inferred for blue monsters range from 100 million to 1 billion solar masses. Given their compact sizes and the available gas supply at their epochs, the star formation efficiency required to produce these objects exceeds 50%. Some early estimates from CEERS data push toward 100%, every atom of available gas becoming a star. No known physics achieves this. The feedback mechanisms that limit efficiency to 10% in the modern universe should have been operating in the early universe as well. If anything, the denser conditions of the early cosmos should have made feedback more effective. The gas was hotter. The radiation fields were more intense, and yet these galaxies converted gas to stars at 5 to 10 times the expected rate. Something suppressed the feedback, or something accelerated the collapse. Nobody has identified what that process was. The blue monsters raised the stakes of the JWST anomalies from a question of mass to a question of mechanism. It was no longer enough to say the early galaxies were surprisingly large. Now the question was, how? How did physics work differently in the first few 100 million years? And the blue monsters were not the only evidence that something fundamental had changed. JWST also found chemical signatures in the early universe that should have taken billions of years to appear, starting with an element that has no business existing at the dawn of time. In January 2024, a team led by Stefano Carniani confirmed the redshift of a galaxy designated JADES GSZ 14-0 using roughly 10 hours of near-spec spectroscopy. The redshift came in at 14.32. That made it the most distant spectroscopically confirmed galaxy ever observed, seen as it existed just 290 million years after the Big Bang. 290 million years. To put that in perspective, if you compress the entire history of the universe into a single calendar year, with the Big Bang at midnight on January 1st, JADES GSZ 14-0 would appear on January 8th. The galaxy existed in what cosmologists call the cosmic dawn, the epoch when the first sources of light were just beginning to switch on in a universe that had been dark since recombination. The galaxy spans roughly 1,600 light-years across. Small by modern standards but remarkably well-defined for its epoch, its luminosity and inferred stellar mass both exceed what Lambda CDM predicts for objects at this redshift. But the mass and luminosity were not the biggest surprise. The biggest surprise was what Carniani's team found in the spectrum: oxygen. At 290 million years after the Big Bang, the universe was supposed to contain almost nothing except hydrogen and helium, the two elements forged in Big Bang nucleosynthesis during the first few minutes of existence. Heavier elements, which astronomers call metals regardless of whether they are actually metallic, are produced inside stars through nuclear fusion. When those stars die, they scatter those elements into the surrounding gas through stellar winds and supernova explosions. The next generation of stars forms from this enriched gas, lives and dies, and enriches the gas further. Each generation adds to the chemical complexity of the universe. Oxygen is the third most abundant element in the cosmos today, after hydrogen and helium. It is produced primarily in the cores of massive stars, those above roughly 8 times the mass of our star, through the carbon-nitrogen-oxygen fusion cycle. These massive stars live fast and die young, typically within 5 to 10 million years. But producing detectable oxygen in a galaxy requires multiple generations of massive stars, living, dying, and seeding the interstellar medium with progressively more enriched material. The standard timeline for this process allows for hundreds of millions of years at minimum. Finding oxygen at 290 million years after the Big Bang compresses that timeline almost to its breaking point. Some models can accommodate it, barely, by invoking extremely massive first-generation stars that formed immediately and died within a few million years, enriching the gas for a rapid second and third generation. But these models require precisely the kind of high star formation efficiency that the blue monsters already demonstrated was problematic, and they require it even earlier, at higher redshifts. JADES, GS, Z, 14.0, held the distance record for nearly 2 years. During that time, it became one of the most studied objects in extragalactic astronomy. Teams analyzed its morphology, its spectral energy distribution, its chemical abundances. Each analysis added detail to a picture that remained stubbornly difficult to explain within the standard framework. Then, in January 2026, the record fell, and the galaxy that broke it was even harder to explain because it contradicted the models and the other record holder simultaneously. The galaxy designated MOME-Z 14 was confirmed in January 2026 at a redshift of 14.44. That pushed it past JWST 14.0 by a slim margin, making it the most distant galaxy ever observed. The light from MOME-Z 14 left its source roughly 280 million years after the Big Bang, just 10 million years earlier than the previous record holder. 10 million years is cosmologically insignificant. At these redshifts, the difference between 14.32 and 14.44 corresponds to a sliver of time barely distinguishable in the models. What made MOME-Z 14 remarkable was its size, or rather, its lack of size. JWST 14.0 measures roughly 1,600 light-years across. MOME-Z 14 measures approximately 240 light-years across, nearly 7 times smaller. Two galaxies existing at essentially the same moment in cosmic history, separated by an insignificant gap in time, and yet one is almost an order of magnitude larger than the other. This was not supposed to happen. The prevailing models of early galaxy formation predicted that the first galaxies would share broadly similar properties. They would form from similar initial conditions, under similar physical processes, and produce similar results. The cosmic dawn was assumed to be relatively uniform, a period when the first structures emerged from nearly identical seeds scattered by quantum fluctuations in the early universe. Finding two galaxies at redshift 14 with wildly different sizes destroys that assumption. The diversity of the earliest galaxies implies that multiple formation pathways were already operating when the universe was barely 280 million years old. Whatever process built JADES GSZ 14.0 into a 1600 light-year structure did not operate the same way for MOMZ 14. And whatever compressed MOMZ 14 into a 240 light-year package did not affect its neighbor at nearly the same epoch. This matters because it means the earliest moments of galaxy formation were more complex than any model anticipated. A single explanation for the anomalies, whether top-heavy stellar populations, unusual gas accretion, or anything else, would need to account for objects being dramatically different from each other, spanning a huge range of sizes at the same epoch. The problem is not that the early universe made galaxies too fast. The problem is that it made several kinds of galaxies too fast through mechanisms that appear to have produced a range of outcomes that the models cannot reproduce. MOMZ 14 is still being studied. Its compactness raises specific questions about its stellar density, its formation mechanism, and whether it contains the same chemical signatures as JADES GSZ 14.0. Spectroscopic analysis is ongoing, and the results will either deepen the diversity problem or reveal some common thread connecting the two record holders. Consider the scale. 240 light-years is roughly the distance from our star to Arcturus and back. 60 times over. That is the entire width of a galaxy that formed when the observable universe was smaller than the distance between the Milky Way and the Andromeda Galaxy today. But JWST was not done pushing boundaries. Before the telescope reached deeper into cosmic dawn, it had already found something closer in time, but far more disturbing in its implications. A black hole that sat at the center of a galaxy 470 million years after the Big Bang. And this black hole weighed as much as every star in its galaxy combined. The galaxy is called UHZ1. It sits at a redshift of approximately 10.1, which places it 470 million years after the Big Bang. JWST did not observe it directly. UHZ1 lies behind galaxy cluster Abell 2744, one of the most massive galaxy clusters known. The cluster's gravity bends spacetime around it and acts as a natural magnifying glass. This is gravitational lensing, first predicted by Einstein, and now routinely used to observe objects too faint or too distant for any telescope to see on its own. Abell 2744 amplified the light from UHZ1 by a factor of roughly 4. JWST's infrared cameras identified the lensed galaxy, but identifying it was only the first step. The critical observation came from Chandra, NASA's X-ray Space Observatory, which has been operational since 1999. Chandra stared at the same patch of sky for more than 2 weeks straight, accumulating photon by photon, a faint X-ray signal from an object whose light had traveled 13.2 billion years to reach the detector. 2 weeks of exposure time for a handful of X-ray photons, each one carrying information about conditions in a galaxy that existed when the universe was 3% of its current age. The X-ray emission told the team, led by Priyamvada Natarajan at Yale University, that UHZ1 harbored an active galactic nucleus. A supermassive black hole was feeding on surrounding material, heating it to temperatures that produce X-rays. This alone was notable at such an early epoch. But the mass estimate is what made the result extraordinary. The black hole at the center of UHZ1 weighs approximately 40 million times the mass of our star. That is large for any black hole. But the real number is the ratio. In the local universe, supermassive black holes typically account for about 0.1% of their host galaxy's total stellar mass. The black hole at the center of the Milky Way, Sagittarius A star, weighs 4 million solar masses inside a galaxy of several hundred billion. It is a tiny fraction of the total. UHZ1's black hole weighs as much as every star in its galaxy combined. The ratio is not 0.1%. It is somewhere between 10 and 100%. That is 100 to 1,000 times higher than any local universe relationship predicts. This cannot be produced by the standard model of black hole growth. In the conventional picture, supermassive black holes start as stellar mass seeds, the remnants of massive stars that collapse at the end of their lives. These remnants weigh perhaps 100 solar masses. These seeds then grow by accreting surrounding material. But accretion has a speed limit called the Eddington limit, the point at which radiation pressure from the infalling material pushes back against further accretion. At the Eddington rate, a 100 solar mass seed needs well over 600 million years to reach 40 million solar masses. UHZ1's black hole did it in 470 million years, and that is only if it started accreting the instant it formed, which is physically unrealistic. Natarajan's team published their findings in Nature Astronomy in late 2023. The paper did not merely report a large black hole, it reported a black hole that could not have formed through any known growth mechanism in the available time. And if it could not have grown to this size, it had to have started bigger, much bigger, which meant the origin story for supermassive black holes needed to be completely rewritten. The standard origin story goes like this. A massive star, perhaps 20 or 30 times the mass of our star, exhausts its nuclear fuel and collapses. The core implodes into a black hole weighing maybe 100 solar masses. Over hundreds of millions of years, this stellar mass black hole drifts toward the center of its galaxy, merges with other black holes, and accretes gas from its surroundings. Gradually, limited by the Eddington rate, it grows. After billions of years, it becomes the supermassive black hole we observe at the centers of modern galaxies. This process is called light seed accretion, and it has been the default explanation for decades. UHZ1 broke it. 40 million solar masses in 470 million years from a 100 solar mass seed is mathematically impossible at the Eddington rate. Even allowing for brief episodes of super Eddington accretion, where the black hole temporarily exceeds its theoretical feeding limit, the numbers do not work. You cannot grow that much mass that quickly from a small starting point. Natarajan's team proposed an alternative. In the very earliest universe, before any stars had formed, vast clouds of primordial gas existed that contained no metals whatsoever. Metals are critical in star formation because they allow gas to cool efficiently. Without metals, cooling is inefficient, and the gas cloud does not fragment into smaller pieces the way metal-enriched gas does. Instead, the entire cloud can collapse coherently under its own gravity. If the cloud is massive enough and no fragmentation occurs, the result is not a star, it is a black hole. This is the direct collapse black hole model, sometimes called the heavy seed scenario. Instead of starting at 100 solar masses and growing slowly, these black holes start at 10,000 to 100,000 solar masses. A heavy seed of 100,000 solar masses, accreting at the Eddington rate from the moment of its formation, can reach 40 million solar masses in the time available before UHZ1's epoch. The math works, but the heavy seed model carries an implication that rearranges the conventional relationship between black holes and galaxies. In the standard picture, galaxies form first, and black holes grow inside them. In the direct collapse scenario, the black hole forms first. The galaxy assembles afterward from the leftover gas and material orbiting the seed. The black hole is not a passenger in its galaxy, it is the foundation. This would explain the anomalous mass ratio in UHZ1. If the black hole formed before the galaxy, and the galaxy is still assembling around it, then, at early times, the black hole would dominate the total mass. Over billions of years, as more gas falls in and more stars form, the galaxy would gradually outgrow the black hole. The ratio would fall to the 0.1% we observe locally. The ratio is not anomalous. It is a snapshot of a galaxy still under construction. Natarajan has been developing the heavy seed theory for over 15 years, long before JWST launched. The telescope did not inspire the theory, It provided the first observational evidence consistent with it. UHZ-1 is exactly the kind of object the direct collapse model predicts. An overly massive black hole sitting inside an undersized galaxy at high redshift. If black holes came before their galaxies, the architecture of the early universe looked nothing like what the standard model assumed, and JWST found an entire population of objects that might be the cocoons where this process played out, objects that match nothing in any catalog, textbook, or simulation. Starting in 2022, astronomers processing JWST survey images began flagging small red sources that did not fit any known classification. They were compact, unresolved, or barely resolved even in JWST's sharp infrared images. They were red, their spectral energy peaked at longer wavelengths, and they were numerous, scattered across every deep field the telescope observed. The initial assumption was straightforward. Small red dots in deep infrared images are usually distant galaxies reddened by dust or by the cosmological stretching of light known as redshift. Astronomers tagged them for follow-up and moved on to higher priority targets. By 2024, follow-up spectroscopy had begun, and the little red dots, as the community informally named them, turned out to be something unexpected. Their spectra showed features consistent with active galactic nuclei. Each one appeared to harbor an actively feeding supermassive black hole, but their sizes were wrong. Each one measured less than 1,000 light-years across. For a galaxy hosting an active supermassive black hole, that is absurdly compact. Most AGN-host galaxies in the local universe span tens of thousands of light-years. By 2025, 341 little red dots had been catalogued across multiple surveys. They concentrate between redshifts 5 and 10, corresponding to a window from about 500 million to 1 billion years after the Big Bang. Their AGN number densities, meaning the number of active black holes per unit volume of space, exceed predictions from every existing model by a factor of 50. 50 times more active black holes than any simulation produced, and then they vanish. Below redshift 5, the little red dots disappear. No counterpart exists in the local universe. No known type of galaxy, AGN, or compact object in the nearby cosmos matches their properties. An entire population of objects appeared, persisted for roughly 2 billion years of cosmic time, and then ceased to exist without leaving any identifiable descendants. 341 objects matching nothing. That fact alone would make the little red dots one of the most significant discoveries in extragalactic astronomy. But the Rubies survey, analyzing these objects in detail through 2024, found something inside one of them that elevated the mystery from strange to inexplicable. The Rubies team identified a particular little red dot at redshift 3.55 and examined its spectrum carefully. What they found was a Balmer break, a sharp drop in brightness at a specific wavelength caused by hydrogen atoms absorbing photons of particular energies. Balmer breaks are among the most well-understood features in all of spectroscopy. They are diagnostic tools. They tell astronomers the age, temperature, and composition of a stellar population. Astrophysicists have been using Balmer breaks to characterize galaxies for decades. This Balmer break matched nothing. Not a galaxy template, not a standard AGN spectrum, not a quasar, not any combination of known sources. The spectral signature dropped off what the team described as a cliff into territory where no existing model could reproduce the shape. They named it accordingly. The cliff at redshift 3.55 is a spectral feature that belongs to an object for which no theory exists. It sits inside a class of objects that has no counterpart in the modern universe. And a researcher at Penn State was about to bet his career on an explanation that had never appeared in any textbook. Joel Lager is an astrophysicist at Penn State who had been studying the spectral properties of galaxies across cosmic time. In September 2024, he proposed an explanation for the little red dots that broke with every existing classification scheme. The little red dots, Leha argued, are not galaxies at all. They are something that has never been observed before. He called them black hole stars. The concept works like this. In the early universe, a massive cloud of pristine gas collapses directly into a black hole following the heavy seed mechanism that Natarajan described for UHZ-1. But instead of the surrounding gas immediately accreting or dispersing, a substantial envelope of gas remains around the newborn black hole. The black hole heats this envelope from within through radiation from its accretion disk. The heated gas glows. It emits light across a broad range of wavelengths. From a distance, the object looks like a galaxy. It has the luminosity of billions of stars. It is compact. It is red, but it is not a collection of stars. It is a single black hole wrapped in a cocoon of hot gas. A black hole star would explain several properties of the little red dots simultaneously. Their extreme compactness becomes natural. There is no galaxy to be extended. There is only a gas cocoon, which can be as small as a few hundred light years across. The strange spectra, including the cliff, become interpretable as the emission of a heated gas envelope rather than a stellar population. No template for a stellar population can match the spectrum because there is no stellar population. The Balmer break is being produced by hydrogen in the cocoon, not in the photospheres of billions of individual stars. The vanishing act also finds an explanation. Gas cocoons are temporary structures. Over time, the black hole either accretes the remaining gas or radiation pressure blows it away. Once the cocoon dissipates, what remains is a naked supermassive black hole. Without the glowing envelope, the object becomes invisible at optical and near-infrared wavelengths. It is still there. It simply stopped emitting in ways that JWST can detect. The little red dots did not die. They shed their cocoons and went dark. If Leha is right, 341 objects in JWST data represent a phase of black hole evolution that nobody had ever theorized before the data forced its invention. An entire category of astrophysical object, visible only during a brief window of cosmic time, that had been completely absent from every model and textbook. The implications extend beyond classification. If these are black hole cocoons, then supermassive black holes in the early universe were even more common than the already elevated AGN densities suggest. Every little red dot is a direct collapse black hole in its chrysalis stage. Leja's hypothesis remains unconfirmed. Spectroscopic tests are ongoing. The theory makes specific predictions about emission line ratios and spectral shapes that can be checked against the data. Confirmation would require ruling out every alternative explanation for the little red dots, and several alternatives still compete for attention. But the black hole star idea was not the most radical proposal on the table. Another team had been working on a theory that went even further, suggesting that some of JWST's most distant objects are individual stars of almost inconceivable mass, kept alive by a fuel source that physics has never directly observed. Dark matter. The idea came from Catherine Fries at the University of Texas at Austin. In 2007, years before JWST launched, Fries and her collaborators published a theoretical framework for what they called dark stars. The name is misleading. They are not dark. They are among the brightest objects the theory predicts. The dark refers to their fuel source. In standard stellar physics, stars burn through nuclear fusion. Hydrogen atoms slam together at millions of degrees, fuse into helium, and release energy. Dark stars would not. They would be powered by the annihilation of dark matter particles inside a primordial gas cloud. Dark matter makes up roughly 27% of the universe's total energy content. It has never been directly detected. No instrument has ever captured a dark matter particle, but its gravitational effects are measurable everywhere. Galaxies rotate too fast for the visible matter they contain. Galaxy clusters hold together with far more force than their luminous mass can explain. Something invisible is doing the work. Fries's proposal was specific. In the earliest epoch of the universe, before any normal stars had formed, dense halos of dark matter would have collected around clumps of primordial gas. If dark matter consists of particles that can annihilate when they collide with each other, which several leading candidates predict, then those annihilations would release energy into the gas cloud, enough to heat it, enough to prevent it from collapsing into a normal star. Instead of a compact, hot object burning fusion fuel, you would get something enormous, a single star with a mass up to 1 million times that of our star, as luminous as an entire galaxy. And here is where JWST enters the picture. When astronomers point the telescope at the most distant objects in the universe, they see bright, compact sources at extreme redshifts. They assume those sources are galaxies containing millions or billions of stars. But a dark star of 1 million solar masses would look almost identical in JWST imaging data. Same brightness, same compactness, same redshift. You cannot tell them apart with images alone. In 2023, Fries's team flagged 3 photometric candidates in JWST data consistent with the dark star model. The objects had been classified as early galaxies. Their brightness and color profiles matched what dark star theory predicted, but photometry only tells you how bright something is and what color it appears. It cannot tell you what the object actually is. For that, you need spectroscopy. You need to split the light into its component wavelengths and read the chemical fingerprint. Photometry is a photograph. Spectroscopy is a blood test. And in 2023, nobody had the spectroscopic data to confirm or rule out dark stars in those candidates. They could be galaxies. They could be something that had never been observed before. The distinction mattered enormously. If even a fraction of JWST's most distant galaxies turned out to be individual dark stars, the census of the early universe would need rewriting from the ground up. The number of galaxies at high redshift would drop. The inferred star formation rates would change. The impossible masses that launched the entire crisis might partially dissolve because some of those bright dots were never collections of stars at all. They were single objects, burning a fuel that physics has spent decades trying to detect. Spectroscopy was the only path forward, and in October 2025, a spectral line appeared that nobody had expected to find. The target was JADES GSZ 140, the most distant spectroscopically confirmed galaxy in existence, sitting at redshift 14.32. Light that left this object when the universe was just 290 million years old. The Stefano Carniani's team had already confirmed its redshift using roughly 10 hours of near-infrared spectrograph observations. They had detected oxygen in its spectrum, which was strange enough. But a separate analysis of that same spectral data, published in October 2025, found something else buried in the signal, a tentative absorption feature at 1,640 angstroms, helium-2 absorption. To understand why this matters, you need to know what helium-2 is. Regular helium has 2 electrons. Ionize it once, strip away 1 electron, and you get helium-1. Ionize it again, strip away the second, and you get helium-2. Fully ionized helium, the energy required is extreme. You need photons with wavelengths shorter than 228 angstroms, which means temperatures far beyond what normal stellar populations produce at this epoch. In the modern universe, you find helium-2 emission near the most violent objects, quasars, Wolf-Rayet stars, active galactic nuclei. But at redshift 14, 290 million years after the Big Bang, none of those sources should exist yet. Normal stars at this epoch would have been predominantly hydrogen-burning. incapable of producing the hard ultraviolet radiation needed to doubly ionize helium. And yet, there it was. A dip in the spectrum at exactly 1,640 angstroms. The dark star model predicts exactly this signature. The extreme temperatures generated by dark matter annihilation inside a supermassive dark star would naturally produce hard ultraviolet radiation capable of ionizing helium twice over. A dark star of several 100,000 solar masses would show helium-2 absorption at precisely this wavelength. The signal is tentative. The signal-to-noise ratio hovers around 2, which in astronomy means you can see it, but you cannot bet your career on it. A signal-to-noise of 5 is the traditional threshold for a confirmed detection. It could be real. It could be an artifact of the data reduction pipeline. It could be noise that happens to land at an interesting wavelength. But if it is real, the consequences restructure multiple fields simultaneously. It would mean the most distant confirmed object in the universe is not a galaxy. It is a single star, powered by a substance that has never been directly detected. The first observational evidence that dark matter interacts with visible matter in a way that produces light. 27% of the universe caught influencing the objects we can see for the first time. It would also mean that an unknown number of other bright, compact, high redshift objects in JWST data might be dark stars misidentified as galaxies. The early universe's population census could be fundamentally wrong. We assumed we knew what we were looking at. Confirmation requires deeper spectroscopy, more integration time on the same object, or observations of the other dark star candidates. JWST has the capability. The question is whether it gets the telescope time, which is allocated competitively and in high demand. The tentative detection sits in the literature, a whisper at 1,640 angstroms. And while astronomers debated whether JADES GSZ140 might be a dark star, another spectroscopic analysis of a different object was revealing a chemistry problem that had no solution at all. GNZ11 sits at redshift 10.6, 430 million years after the Big Bang. For years before JWST, it held the record as the most distant galaxy ever observed, detected first by the Hubble Space Telescope in 2016. JWST turned its instruments on GNZ11 in 2023, and Roberto Maiolino's team at Cambridge used the near-infrared spectrograph to pull apart its light with unprecedented precision. What they found was nitrogen. Specifically, the ratio of nitrogen to oxygen in GNZ11 was 4 times higher than the ratio measured in our star. This is a problem that sounds technical, but carries a straightforward consequence. Nitrogen, in the amounts detected, cannot be produced quickly. Under standard chemical evolution models, you need intermediate mass stars, objects between roughly 2 and 8 solar masses, to cycle through their entire lifetimes. These stars burn hydrogen, then helium, then produce nitrogen through the carbon-nitrogen-oxygen cycle in their cores. When they die, they expel that nitrogen into the surrounding gas through planetary nebulae and stellar winds. The next generation of stars incorporates it. The nitrogen-to-oxygen ratio builds up gradually, generation by generation, over timescales measured in hundreds of millions to billions of years. 430 million years is not enough. The universe at that age had not existed long enough for multiple generations of intermediate mass stars to live, die, enrich the gas, and build up nitrogen to 4 times the solar ratio. The math does not close. Maiolino's team proposed an alternative source: supermassive stars. Not the dark stars, powered by dark matter that Fries described, but a different class of theoretical object. Stars between 1,000 and 100,000 solar masses, formed through runaway collisions in extremely dense stellar clusters. In environments where young stars are packed close enough together, gravitational interactions can cause them to merge repeatedly. Objects of extraordinary mass build up in just a few million years. These supermassive stars would burn hot and fast. Their interiors would reach temperatures where the carbon-nitrogen-oxygen cycle runs at maximum efficiency and shedding nitrogen-rich winds continuously throughout their short lives. A supermassive star of 10,000 solar masses could enrich its surrounding gas with nitrogen in roughly 1 million years. That is fast enough to explain GNZ 11, but it requires conditions that no simulation has fully reproduced. The stellar densities needed for runaway collisions are extreme. The clusters would need to be far denser than anything observed in the modern universe. Stars packed so close together that collisions become inevitable rather than rare, and supermassive stars of this type have never been directly detected. They remain theoretical objects, invoked because the data demands them, not because anyone has seen one. Necessary, perhaps, but unproven. The nitrogen problem in GNZ 11 was not alone. JADES and CEERS already had oxygen at 290 million years. Now, GNZ 11 had nitrogen at 430 million years. Two different elements, two different objects, two different epochs, both demanding chemical enrichment that outpaces every standard model. Each finding could be treated as an isolated anomaly, a single unusual object with unusual chemistry. But isolated anomalies have a way of accumulating, and the next chemical detection would turn two anomalies into a pattern that could not be dismissed. Polycyclic aromatic hydrocarbons are large molecules built from interlocking rings of carbon and hydrogen atoms. The name is technical, but the substance is common. On Earth, you encounter them in barbecue, smoke, diesel exhaust, and charred meat. In space, they are everywhere. They fill the gaps between stars. They coat the surfaces of meteorites. They are so abundant in the Milky Way that their spectral signatures show up in nearly every observation of the interstellar medium. Astronomers know how polycyclic aromatic hydrocarbons form. Carbon-rich stars in the asymptotic giant branch phase of their evolution shed their outer layers in slow, dense winds. As that material cools and expands, carbon atoms bond into increasingly complex structures. Rings form, rings connect to other rings. Over time, the interstellar medium becomes enriched with these molecules. The process requires evolved stars, which means it requires time. Asymptotic giant branch stars are not young. They are intermediate mass stars in the final stages of their lives, after they have burned through hydrogen and helium and begun expelling their outer envelopes. To reach this stage, a star of a few solar masses needs somewhere between 100 million and several billion years. Then the molecules themselves need time to accumulate in sufficient quantities to show up in spectroscopic observations. The conventional estimate for a galaxy to develop a detectable polycyclic aromatic hydrocarbon signature was roughly 1 billion years of stellar evolution. Enough generations of asymptotic giant branch stars living, dying, and seeding the gas with carbon molecules. JWST detected polycyclic aromatic hydrocarbons at redshift 6.7. The universe at that redshift was approximately 900 million years old. That is barely within the theoretical minimum, and only if you assume the most generous possible conditions. Stars forming immediately after the Big Bang, the fastest possible evolution to the asymptotic giant branch phase, maximum carbon yield per star, efficient mixing of enriched material into the surrounding gas, every parameter pushed to its optimum, and even then, the numbers are tight. 900 million years is not a comfortable margin, it is a razor's edge. Now lay the three chemical detections side by side. Oxygen at 290 million years in JADES/GSZ140, nitrogen at 430 million years in GNZ11, polycyclic aromatic hydrocarbons at 900 million years at redshift 6.7. 3 independent chemical signatures detected in 3 different objects at 3 different epochs by 3 different analysis teams. Each one individually pushed the limits of what standard stellar evolution allows. Together, they say something that none of them says alone. The early universe's chemistry was mature almost from the start. It did not build up slowly over billions of years, the way textbooks describe. Complex elements and complex molecules appeared in the first few 100 million years, as though the chemical clock started running before the universe gave it permission. This was no longer a galaxy formation problem. It was no longer a black hole growth problem. The chemistry of the early cosmos was wrong too. Every timeline that cosmology relied on, for stars, for galaxies, for black holes, for dust, for molecules, was landing shorter than the observations demanded. And if the timeline was wrong for the objects inside the universe, that raised an obvious question about the biggest timeline measurement in all of cosmology, the one that tells us how fast the universe itself is expanding, because that number was in trouble too. There is a number in cosmology that measures how fast the universe is expanding. It is called the Hubble constant, named after Edwin Hubble, who first demonstrated in 1929 that distant galaxies are moving away from us, and that the farther away they are, the faster they recede. The Hubble constant expresses this rate. Its units are kilometers per second per megaparsec. For every megaparsec of distance, roughly 3.26 million light-years, a galaxy moves a certain number of kilometers per second faster. Measuring this number should be straightforward. It is not. For decades, the problem was that nobody could measure it precisely enough. Different methods gave wildly different answers. Estimates fell anywhere from 50 to 100. By the 2000s, precision improved dramatically. 2 approaches emerged as the gold standard. The first is the local distance ladder. Adam Riess, who shared the Nobel Prize in 2011 for discovering the accelerating expansion of the universe, leads the supernova H0 for the equation of state team. His method uses Cepheid variable stars as distance markers. Cepheids are stars that pulse with a period directly related to their intrinsic brightness. Measure the pulse period, calculate the true brightness, compare it to the observed brightness, and you get the distance. Calibrate enough Cepheids, then use them to calibrate type 1a supernovae at greater distances, and you can build a ladder that reaches across the observable universe. Riess's team gets 73.0 kilometers per second per megaparsec. The second method skips the local universe entirely. The Planck satellite, operated by the European Space Agency from 2009 to 2013, mapped the cosmic microwave background. This is the afterglow of the Big Bang itself. Radiation released when the universe was just 380,000 years old. By analyzing the precise pattern of temperature fluctuations in that radiation, physicists can extract a prediction for what the Hubble constant should be today, assuming the standard cosmological model is correct. Planck gets 67.4, 73 versus 67.4, an 8% gap. For years, the assumption was that one of these measurements had to contain a systematic error. Maybe the Cepheid distances were wrong. Maybe dust was reddening the light. Maybe stellar crowding in other galaxies was throwing off the brightness measurements. The Hubble Space Telescope's resolution was limited, and in distant galaxies, individual Cepheids could blend with neighboring stars. That would inflate their apparent brightness and skew the distances. This was a reasonable objection. JWST eliminated it. The telescope's infrared instruments and superior angular resolution could resolve individual Cepheids in galaxies where Hubble saw blurs. Riess's team re-observed the same Cepheid fields with JWST and compared the results. The mean discrepancy between Hubble and JWST Cepheid measurements was 0.03 magnitudes. To explain the tension between 73 and 67.4, you would need a systematic error of 0.18 magnitudes. The actual discrepancy was 6 times smaller than what the critics needed. JWST confirmed the local measurement, 72.6 plus or minus 2.0. The Hubble tension is real. It is not a calibration problem. It is not instrument noise. Two of the most precise measurements in the history of physics, measuring the same quantity, disagree at a statistical significance of 5 sigma, and then a massive instrument in the Arizona desert made it worse. Wendy Friedman has spent decades trying to resolve this argument. She leads the Carnegie-Chicago Hubble program, and her approach deliberately avoids the Cepheid method that RES uses. Instead, her team measures distances using the tip of the red giant branch method. Red giant stars, when they reach a specific phase of helium ignition in their cores, all achieve nearly the same peak luminosity. This makes them a standard candle, just like Cepheids, but one that is less sensitive to dust and crowding, because red giants are intrinsically brighter in the infrared and easier to isolate in crowded fields. Friedman's result, somewhere between 69 and 72 kilometers per second per megaparsec, right between RES and Planck. On the surface, this should help narrow things down. A third independent measurement, landing between the other two, might point toward the true value. It did the opposite. Friedman's number does not confirm RES. If the tip of the red giant branch method is more reliable than Cepheids, then the local Hubble constant is lower than 73, and RES has a systematic error his team has not found. But Friedman's number does not confirm Planck either. 69 to 72 is still higher than 67.4. The cosmic microwave background prediction remains too low. Instead of 2 camps, there are now 3. Each team has spent years refining their methods. Each team accuses the others of unresolved systematic errors. RES says the Cepheid calibration is solid, and JWST proved it. Friedman says her method is cleaner and less assumption-dependent. Planck's team says the cosmic microwave background measurement is the most fundamental because it relies on physics, not on local distance calibrations that can go wrong in 100 subtle ways. The disagreement is not just scientific. Careers have been built on these measurements. Grant funding flows toward teams that can claim the most precise value. Tenure decisions, conference invitations, and publication prestige all ride on whose number is right. Admitting a systematic error would mean admitting that years of work contained a flaw that the team failed to catch. Nobody volunteers for that. The institutional dynamics are real, and they slow down resolution. But behind the human politics, a deeper question remains. What if none of the measurements are wrong? What if 73 and 67.4 and 69 to 72 are all correct, each measuring the expansion rate at a different epoch or through a different physical pathway, and the reason they disagree is that the model connecting them is broken? The standard cosmological model, Lambda cold dark matter, predicts a specific relationship between the early universe's expansion rate and today's expansion rate. If that model is correct, the cosmic microwave background value and the local value must agree. They do not. If the model is wrong, they would not have to agree. And the disagreement would not be an error to fix. It would be evidence. Evidence that something about the bridge between the early universe and the late universe is missing from the equations. The Hubble tension sat in this unresolved state for years. Both sides dug in. JWST confirmed the local side. Planck remained solid on the early side. The gap persisted. And then, in March 2024, a different instrument produced data that suggested the bridge between early and late universe might indeed be broken, in a way nobody had anticipated. The Dark Energy Spectroscopic Instrument, sits at the Mile Telescope on Kitt Peak in southern Arizona. It is not a space telescope. It is a ground-based machine designed for one purpose: to map the three-dimensional positions of tens of millions of galaxies and quasars across 11 billion years of cosmic history. Its instrument is built around 5,000 robotic fiber optic positioners, each one capable of independently targeting a different object in the telescope's field of view. In a single exposure, it can simultaneously collect the spectra of 5,000 galaxies. Over its planned 5-year survey, it will map roughly 40 million objects, constructing the most detailed map of the universe's expansion history ever assembled. The quantity it measures is the baryon acoustic oscillation signal. In the first few 100,000 years after the Big Bang, sound waves propagated through the hot plasma of the early universe. When the plasma cooled and the universe became transparent, those sound waves froze in place, leaving a characteristic spacing in the distribution of galaxies. That spacing acts as a cosmic ruler. Measure how it appears at different redshifts, and you can track how the universe has expanded over time. In March 2024, the instrument released its Year 1 results. The team had mapped roughly 6 million galaxies and quasars from the first year of observations. When they fitted the data to a cosmological model, something unexpected appeared. The equation of state parameter for dark energy, labeled W0, came out at -0.752 plus or minus 0.057. In the standard lambda cold dark matter model, this parameter should be exactly -1. -1 means dark energy is a cosmological constant. It does not change. It has the same strength everywhere, at all times, from the beginning of the universe to its end. Albert Einstein introduced it in 1917 and later called it his greatest blunder. In 1998, two teams independently discovered the universe's expansion is accelerating, and the cosmological constant was resurrected as the explanation. For 25 years, W equals -1 has been the default assumption. -0.752 is not -1. The Year 1 result was a 2.8 sigma signal. In physics, 2.8 sigma means there is roughly a 1 in 200 chance the deviation is random noise, suggestive but not conclusive. Most anomalies at this significance level disappear with more data, but by January 2026, the instrument had processed more of its survey data. The signal did not disappear, it strengthened. The latest analysis pushed the significance to 4.2 sigma. The threshold for a formal discovery in particle physics is 5 sigma, which corresponds to a 1 in 3.5 million chance of a random fluctuation. 4.2 sigma is not there yet, but it is close. Close enough that the cosmological community cannot ignore it. If dark energy is not a constant, if it is weakening over cosmic time, the consequences ripple through every model of the universe's past and future. The expansion history changes. The relationship between the early and late universe shifts. And perhaps most importantly, it might connect to the other crisis that JWST has been documenting since 2022. Because in November 2025, a paper appeared that drew a line between the expanding universe and the impossible galaxies. The paper, published in November 2025, proposed something that had been whispered about in cosmology seminars, but rarely stated in print. The anomalies JWST keeps finding in the early universe and the Hubble tension measured in the late universe might share a single cause. The logic works like this. If dark energy was stronger in the early universe than it is today, the expansion history between then and now would differ from what lambda cold dark matter predicts. The early universe would have expanded differently. The relationship between redshift and cosmic time would shift. An object observed at redshift 14 would not correspond to 290 million years after the Big Bang. It might correspond to a slightly different age, under slightly different conditions, with slightly different densities and temperatures. That difference, even if small, compounds across every calculation that depends on the expansion history. Galaxy masses, inferred from luminosity, depend on the assumed distance, which depends on the expansion history. Star formation rates depend on the time available. Black hole growth calculations depend on the time between the Big Bang and the observed epoch. Change the expansion history, and you change the denominator in every one of those calculations. The paper used the dark energy spectroscopic instrument's evolving dark energy parameters to construct an alternative expansion model labeled W0 WA cold dark matter. The authors recalculated predicted galaxy populations, star formation rates, and black hole growth timelines under these modified conditions. Several of the JWST anomalies that seemed impossible under lambda cold dark matter became less severe, not fully resolved. The galaxies were still more massive than expected. The black holes were still larger than standard accretion models allow, but the gap between observation and prediction narrowed. The impossible became merely improbable, and the Hubble tension under this same modified expansion history also eased. The predicted early universe value for the Hubble constant shifted slightly, reducing the gap between the Planck measurement and the local measurement. Two separate crises, one in the early universe observed by JWST, and one in the expansion rate measured by competing teams, partially dissolving under the same modification to the same model. When a single change to a theory simultaneously addresses multiple independent problems, it carries more weight than a patch that fixes only one. Patches are cheap, connections are expensive, but elegance is not proof. The modified model introduces new free parameters. More free parameters make any model more flexible, and more flexibility means it can fit more data regardless of whether it is physically correct. Critics pointed this out immediately. You can always improve the fit by adding knobs to turn. The question is whether the knobs correspond to real physics. The dark energy spectroscopic instrument is still collecting data. Its full 5-year survey will not be complete until roughly 2026. Each additional year either strengthens or weakens the 4.2 sigma signal. If it crosses 5 sigma with the full dataset, the case for evolving dark energy becomes difficult to dismiss. And if evolving dark energy truly connects the two biggest anomalies in modern cosmology, the standard model does not need patches. It needs replacement. But replacement with what? The consequences of weakening dark energy extend far beyond galaxy formation and expansion rates. They reach all the way to the end. For 25 years, the default picture of the universe's future has been defined by the cosmological constant. If dark energy maintains its current strength indefinitely, the expansion of the universe will continue to accelerate. Galaxies outside our local group will recede faster and faster. Their light will redshift beyond detection. One by one, they will cross the cosmic horizon and disappear from view. Given enough time, the observable universe will shrink to our local cluster of galaxies, then to our single merged galaxy, then to isolated stellar remnants cooling in an expanding void. This is the heat death scenario, not a dramatic explosion. A slow fade to maximum entropy, where every usable source of energy has been exhausted and the universe drifts toward absolute cold over timescales measured in trillions of years. Some versions of this scenario are more violent. If dark energy were to strengthen over time rather than remain constant, the acceleration would eventually tear apart galaxy clusters, then galaxies, then stellar systems, then atoms. This is the Big Rip, a hypothetical endpoint where the expansion rate becomes infinite in finite time. Both of these outcomes assume dark energy stays the same or gets stronger. The dark energy spectroscopic instrument's data suggests the opposite. Dark energy appears to be weakening. If W0 is truly negative, 0.752, and trending in the direction the data indicates, then the accelerating expansion will not continue indefinitely. At some point in the far future, dark energy's push will diminish below the threshold where it overpowers gravity. Gravity, which has been losing the tug-of-war against dark energy for the past 5 billion years, would begin to win again. The expansion would slow, then stop, then, potentially, reverse. The universe would begin to contract, slowly at first, then faster. Galaxies that had been racing apart would begin falling toward each other. The temperature of the background radiation would rise as space itself compressed. Structures that took billions of years to form would be crushed back together. The endpoint, carried to its logical extreme, would be something like the reverse of the Big Bang, a collapse to a singularity. The Big Crunch. This is speculative. The extrapolation from current data to cosmic endpoint spans timescales that dwarf the current age of the universe. Small uncertainties in today's measurements amplify into enormous uncertainties in predictions that extend 20 or 50 or 100 billion years into the future. No physicist would stake their reputation on a specific timeline, but the direction matters. For a quarter century, the assumption has been that the universe expands forever. The dark energy spectroscopic instrument's data does not confirm that assumption. Combined with JWST's evidence that the early universe was radically different from what models predicted, a new picture is forming. The universe might not be an eternal expansion. It might have a beginning, a middle, and an end. And the early universe that JWST is revealing, with its impossible galaxies and premature chemistry and oversized black holes, might be telling us something about the conditions at the beginning that we have never properly understood, because JWST was not finished. The most distant galaxies and black holes were only part of the story. The telescope also found structures at scales larger than individual galaxies, appearing billions of years ahead of schedule. Return to the 6 galaxies from the CEERS survey, the ones that launched the crisis in February 2023. After the overcounting scandal, after the recalibrations and spectroscopic confirmations, the revised masses came down. The original estimates of 10 to 100 billion solar masses were inflated. The corrected values were lower. Critics declared victory. Headlines moved on. The crisis was over, except the revised masses were still too high. In 2025, the Renaissance simulations, one of the most sophisticated cosmological simulation suites ever built, attempted to reproduce the JWST observations within the standard Lambda cold dark matter framework. The team used a specific modification, a top-heavy initial mass function. In standard stellar physics, when a cloud of gas collapses and fragments into stars, the resulting population follows a predictable distribution. Lots of small stars, fewer medium stars, very few massive stars. This distribution, called the initial mass function, has been measured in the Milky Way and appears to be roughly universal. The Renaissance simulations proposed that in the early universe, conditions were different enough to shift this distribution. More massive stars per cloud, fewer small ones, a top-heavy function. The effect on inferred galaxy masses is significant. When you observe a distant galaxy, you measure total light output and convert it to stellar mass using assumptions about the mix of stars present. If the mix skews toward massive, luminous stars, you need fewer total stars to produce the same light. The inferred mass drops. The Renaissance team showed that a top-heavy initial mass function could reduce the inferred masses of JWST's anomalous galaxies by roughly a factor of 10, enough to bring some of them within the range lambda cold dark matter allows. This was presented as evidence that the standard model can survive, and it might. But the argument has a circular quality that critics were quick to identify. The initial mass function has been measured locally and appears universal. Invoking a non-universal mass function specifically to save the model is not independent evidence. It is a patch designed to produce the needed result. If the early universe's initial mass function was truly different, that itself demands an explanation. What physical conditions in the first few 100 million years produced a fundamentally different star formation process? The answer is unknown. The simulation works mathematically. Whether it corresponds to reality is a separate question entirely. Meanwhile, the corrected galaxy masses, even with the most favorable initial mass function assumptions, still sit at the upper edge of what lambda cold dark matter permits. The overcounting scandal made the problem quieter. The Renaissance simulations made it more sophisticated. Neither made it go away. Each anomaly generates a proposed fix. Each fix partially works. And each partial fix leaves a residual that accumulates alongside every other residual from every other partial fix. One unexplained residual is a loose thread, 10 of them, all pointing in the same direction, all demanding that the early universe was more active and more structured than the standard model allows, is something else entirely. For 25 years, astronomers told a simple story about the first billion years. The universe began as a hot, smooth soup of hydrogen and helium. Gravity slowly pulled gas into clumps. Those clumps became the first tiny, metal-poor protogalaxies. Small things merged into bigger things over billions of years. Dust was a late arrival. Metals were a late arrival. Structure was a late arrival. Everything built up gradually, like sediment layering on an ocean floor. JWST found the ocean floor already covered. The sediment was already deep. In 2024, a class of objects called red monsters appeared in the data. They are massive, dusty galaxies sitting inside the first billion years after the Big Bang, and they violate every part of that simple story simultaneously. Each one is nearly the size of the Milky Way. Their dust content is high. Their star formation rates run at double modern levels. And dust is the critical detail, because dust is not simple. Dust is made of metals. Metals are forged inside stars. Stars must live, burn through their fuel, and explode before they scatter metals into the surrounding gas. That gas must cool, collapse, form new stars, and repeat the cycle. Each generation takes hundreds of millions of years. The dust inside a red monster represents the accumulated output of multiple stellar generations that somehow completed their entire life cycle within a window that should not have been long enough for even one. The protogalaxy story said the first billion years would produce small, fragile, metal-starved objects. Instead, JWST found fully operational galactic ecosystems. Dust and metals and structure and size, all present at once, all impossibly early. It is not that one measurement is off. Every measurement is off in the same direction. The early universe was not assembling slowly. It was already assembled. Red monsters sit alongside the impossible massive galaxies from the CEERS survey, but they add a dimension those earlier discoveries lacked. The CEERS galaxies were defined by their stellar mass. Red monsters are defined by their completeness. A galaxy can be massive without being chemically mature. A galaxy can have a lot of stars without having processed those stars through enough generations to produce significant dust. Red monsters have everything. They are not just big, they are finished. They look like galaxies that have been evolving for 5 or 6 billion years, except they exist at an age when the universe had barely celebrated its first billion. The standard patches do not work here. Top-heavy initial mass functions can reduce inferred stellar masses, and that helps with the CEERS problem. But top-heavy initial mass functions do not produce more dust. They produce less. Massive stars burn hotter and faster, and their supernovae are more energetic, which actually destroys dust grains in the surrounding medium rather than creating them. The patch that partially fixes one anomaly makes this one worse. Bursty star formation models face a similar wall. If star formation happens in intense, brief episodes separated by quiet periods, You can build up stellar mass quickly, but building up dust requires continuity. You need sustained chemical enrichment across multiple generations, not a single violent burst. The burst makes stars. It does not make the dust that red monsters clearly contain. So the early universe was not just making stars faster than expected. It was running a complete chemical factory, cycling material through generation after generation of stellar evolution at a pace that no known mechanism can reproduce. And if single galaxies can achieve this, the next question becomes obvious. Could groups of galaxies do it too? The answer arrived from a survey that was not even looking for it. JADE, the JWST Advanced Deep Extragalactic Survey, had been mapping the most distant galaxies in unprecedented detail. Among its targets was a region where galaxies appeared to cluster unusually close together at high redshift. Follow-up observations revealed something that forced the problem to jump up an entire scale. JADES ID1 is a protocluster, not a single galaxy. A gravitationally bound group of 66 or more galaxies, all sitting at roughly 1 billion years after the Big Bang. X-ray observations registered gas between the member galaxies at temperatures exceeding 1 million degrees. Hot, intracluster medium. The kind of superheated gas that forms when galaxies have been gravitationally interacting for extended periods, their halos colliding and shock heating the intergalactic material. The previous record for a structure like this was 3 billion years after the Big Bang. JADES ID1 arrived 2 billion years ahead of schedule. Galaxy clusters are the largest gravitationally bound structures in the universe. The Virgo cluster contains over 1,000 galaxies. The Coma cluster spans roughly 20 million light-years. These structures take enormous amounts of time to assemble because they require galaxies to form first, then fall toward each other under gravity, then virialize into a stable configuration. Each step operates on timescales measured in billions of years, not hundreds of millions. Finding a protocluster with hot intracluster gas at 1 billion years means every step in that sequence happened faster than any simulation can reproduce. This is where the pattern becomes impossible to ignore. Individual galaxies, too massive. Black holes, too heavy. Chemistry, too mature. Star formation, too efficient. 341 unidentifiable objects that vanished. And now, large-scale structure forming billions of years too early. Each anomaly, taken alone, could be treated as an outlier, a statistical fluctuation, a measurement error that would eventually be corrected. Taken together, they point in one direction. The model that predicts when each of these things should appear is consistently wrong, and it is wrong in the same way every time. Everything is too early. Everything is too complete. Everything looks older than the universe allows. The standard model of cosmology, Lambda CDM, was built to explain the large-scale structure of the universe. Its predictions for the cosmic microwave background are extraordinary. Its description of the cosmic web at low redshift matches observations beautifully. It is one of the most successful models in the history of physics. And it cannot produce what JWST sees in the first billion years. Not the galaxies, not the black holes, not the chemistry, not the clusters. Some of these anomalies might yield to clever modifications. The Renaissance simulations showed that top-heavy initial mass functions can reduce inferred galaxy masses by roughly a factor of 10. That helps with one problem. It does not help with dust or clusters or black hole masses or the 341 little red dots or the chemical enrichment timeline or the star formation efficiency measurements. Each patch fixes one leak and ignores the others. But before the question of whether Lambda CDM can survive, there is a more immediate puzzle. The universe transitioned from an opaque fog to transparent space during its first billion years, in a process called reionization. Astronomers thought they understood how it worked. JWST proved they did not. Reionization is one of the great phase transitions in cosmic history. For the first few 100 million years after the Big Bang, the universe was filled with neutral hydrogen. Opaque, light could not travel freely. Then, the first luminous objects began producing ultraviolet photons, ionizing the surrounding hydrogen, clearing bubbles of transparency that gradually merged until the entire universe became see-through. The textbook timeline placed the end of this process somewhere around redshift 6, roughly 1 billion years after the Big Bang. The mechanism was straightforward. Early galaxies and quasars produced the photons. The fog cleared gradually. Simple. JWST found it ended earlier than the models predicted, closer to redshift 9. That is not a small shift. Redshift 9 corresponds to roughly 550 million years after the Big Bang. Moving the endpoint by 450 million years means the universe became transparent far sooner, which means there were far more ionizing photons far earlier than any known source can account for. This is the photon budget crisis. Add up every galaxy JWST has found in the early universe. Add every quasar. Add every active galactic nucleus. Add the little red dots if you assume they are all active galactic nuclei, producing ionizing radiation at maximum theoretical output. The total number of ionizing photons still falls short of what was needed to clear the fog by redshift 9. Something was producing ultraviolet radiation in the early universe that has not been identified. An unknown source of photons, powerful enough to ionize hydrogen across cosmological volumes, that is either invisible to current instruments or belongs to a category of objects that has not been theorized. Dark stars could fill the gap. If Catherine Fries's model is correct, supermassive dark stars, powered by dark matter annihilation, would have been extraordinarily luminous in ultraviolet wavelengths. A single dark star of 1 million solar masses could produce as many ionizing photons as an entire dwarf galaxy. If dark stars were common in the first few 100 million years, they would be precisely the missing source the photon budget needs. They would also be invisible after their dark matter fuel ran out, explaining why no local counterpart exists. The photon budget crisis connects to nearly every other anomaly JWST has uncovered. If there were more luminous sources in the early universe than current models account for, those same sources would contribute to the unexplained brightness that makes early galaxies appear too massive. Some fraction of the impossible stellar mass might not be stellar mass at all. It might be the light from objects that are not galaxies, counted as galaxies because nobody knew to look for anything else. This is the thread that ties the investigation together. The impossible galaxies, the overmassive black holes, the mature chemistry, the early clusters, the little red dots, the photon budget crisis. They are not separate problems. They are symptoms of the same underlying condition. The census of the early universe is wrong. The catalogue of objects that could exist in the early universe was incomplete. JWST is finding things that were never in the inventory. And the total energy output of the early universe exceeds what every object in that inventory can produce, which means the inventory itself is the problem. The evidence no longer points at individual broken predictions. It points at a model that is missing something fundamental. The question is what? Step back from the individual anomalies and map the full scope of what JWST, DESI, and Chandra have collectively revealed in 3 years of observation. 1. Galaxies 10 to 100 times more massive than any model predicted, sitting at redshifts above 10 within the first 500 million years, confirmed across multiple surveys, revised downward after recalibration, still too massive. 2. A supermassive black hole at 470 million years that weighs as much as every star in its host galaxy. Ratio 100 to 1,000 times higher than any black hole in the local universe. Detected through gravitational lensing and 2 weeks of Chandra X-ray observation. 3. oxygen at 290 million years, nitrogen at 430 million years, with a ratio 4 times higher than anything in our own stellar neighborhood, and polycyclic aromatic hydrocarbons at 900 million years. 3 independent chemical signatures, each requiring timescales the universe had not yet provided. 4. Star formation efficiency above 50% in blue monsters, against a universal average of 10%. Some early estimates from CEERS approached 100%. No known feedback mechanism allows this. 5. 341 little red dots between redshifts 5 and 10, matching no known astronomical object, with active galactic nucleus densities 50 times higher than predicted. One of them, the cliff, produces a Balmer break that fits no existing template. The entire population vanished without leaving descendants. 6. A tentative helium-2 absorption line at 1640 angstroms in JADES GSC 140, consistent with a supermassive dark star powered by dark matter annihilation. Signal-to-noise ratio roughly 2. Not proof, a whisper. 7. The Hubble tension confirmed as real by JWST, with local measurements at 73 km per second per megaparsec and cosmic microwave background measurements at 67.4, a gap of 8% at 5 sigma significance that is not caused by instrument error. 8. Dark energy showing signs of weakening over cosmic time, with DESI measuring the equation of state parameter at negative 0.752 instead of negative 1, now at 4.2 sigma significance and approaching the 5 sigma discovery threshold. 9. A protocluster of 66 or more galaxies with million-degree intracluster gas at 1 billion years, 2 billion years before any simulation predicted such a structure could exist. 10. More ionizing photons in the early universe than every known source combined can produce. An unidentified contributor to reionization that cleared the cosmic fog earlier than any model accounts for. 10 independent anomalies, discovered by different teams using different instruments across different redshifts. Each one challenges a specific prediction of the Lambda CDM model. Together, they describe a universe that was far more complex, far more energetic, and far more structured in its first billion years than the reigning model of cosmology allows. Any one of these could be a fluke. Any two might be coincidence. But 10 anomalies, all pointing in the same direction, all saying the early universe was more advanced than predicted, is a pattern. And the question the pattern raises is not about galaxies or black holes or chemistry. It is about whether the model that has governed cosmology for 25 years can survive what JWST has found. The model has defenders, and their arguments are not trivial. Lambda CDM has been the standard model of cosmology since the late 1990s. It describes a universe composed of roughly 5% ordinary matter, 27% dark matter, and 68% dark energy, expanding from a hot initial state, according to general relativity. Its predictions for the cosmic microwave background match observations to extraordinary precision. Its description of large-scale structure at low redshift, the cosmic web of filaments and voids, is confirmed by galaxy surveys spanning millions of objects. It predicted the accelerating expansion of the universe before supernovae confirmed it. By almost any measure, Lambda CDM is one of the most successful physical models ever constructed. An entire generation of cosmologists built their careers on it. Grants were written against its predictions. Tenure cases were argued on its framework. Textbooks were organized around its timeline. The intellectual and institutional investment in Lambda CDM is immense, and that investment is not purely scientific. It is personal and professional. Declaring a crisis in the foundational model of your field is not a neutral scientific act. It has consequences for funding, for reputation, for the validity of decades of published work. The resistance to abandoning Lambda CDM is not irrational. It is human, and the resistance has produced real results. The Renaissance simulations, published in 2025, demonstrated that incorporating top-heavy initial mass functions into Lambda CDM can reduce the inferred stellar masses of early galaxies by roughly a factor of 10. A top-heavy initial mass function means the first generation of stars were predominantly massive rather than following the distribution observed in the local universe. If early stars were heavier on average, fewer of them would produce the same amount of light. The galaxies would appear less massive than photometry initially suggested. This matters. It means some of the most headline-grabbing claims from 2023 were genuinely overcounted. The media reported impossible galaxies because the mass estimates were inflated by calibration errors and assumption errors. The corrections brought some objects back within Lambda CDM's tolerance. The overcounting scandal was real, and it damaged the credibility of the crisis narrative. But it did not make the crisis disappear. The corrected masses are still too high. Reduced by a factor of 10, yes. But Lambda CDM's predictions were exceeded by factors of 10 to 100. Cut in half, the anomaly remains. The correction made the problem less dramatic. It did not make the problem go away. It made it quieter, and quieter problems in science are dangerous because they stop receiving attention while continuing to exist. The patches also introduce new tensions. Top-heavy initial mass functions help with stellar masses but worsen the dust problem. Bursty star formation models help with star formation rates but cannot explain chemical enrichment timelines. Early dark energy models help with the Hubble tension but have not been shown to resolve the galaxy formation crisis. Each patch addresses one symptom and is silent on the others. No single modification to Lambda CDM has been proposed that simultaneously resolves all 10 anomalies. Not one. And there remains a class of objects that resists every proposed patch entirely. Objects that cannot be explained by recalibration, or different mass functions, or modified star formation histories. Objects that appear to require something genuinely new, 341 of them. Return to the little red dots one more time, because their story has changed since the last time they appeared in this investigation. When they first surfaced in 2022, astronomers catalogued them as compact, high redshift galaxies. Small, red, unremarkable, except for their numbers. By 2024, spectroscopic follow-up revealed they were anything but unremarkable. Their active galactic nucleus densities were 50 times higher than any prediction. Their spectra did not match galaxies or quasars or any known template. The cliff produced a Balmer break that sits in empty theoretical space, and the population is bounded. They appear around redshift 10 and cluster densely between redshifts 5 and 8. Below redshift 5, they vanish, not gradually, completely. No astronomical population behaves like this. Galaxies evolve. They merge, they grow, they change color and morphology, but they leave descendants. Elliptical galaxies descend from merged spirals. Spiral galaxies descend from turbulent disk systems. Every type of galaxy observed in the local universe can be traced backward to a precursor population. The little red dots cannot be traced forward to anything. Whatever they are, they stopped being it, and nothing recognizable replaced them. Joel Lager's black hole star hypothesis offers the cleanest explanation available. If little red dots are direct collapse black holes wrapped in heated gas cocoons, their disappearance is natural. The cocoon is temporary. Dark matter and primordial gas funnel onto the collapsing object, heating the surrounding envelope to temperatures that produce emission, mimicking a stellar population. From the outside, through JWST's instruments, it looks like a compact galaxy, but it is one object, one enormous black hole accumulating mass inside a glowing shell. The cocoon phase lasts as long as the fuel supply holds. When the surrounding gas is consumed or dispersed by the black hole's own radiation, the cocoon fades. What remains is a naked, supermassive black hole, invisible at optical and near-infrared wavelengths. The little red dot did not evolve into something else. It shed its skin. The chrysalis dissolved, leaving only the black hole at the center, which then became the seed around which a proper galaxy eventually formed. If this is correct, the relationship between black holes and galaxies is inverted. The standard picture says galaxies form first, and black holes grow later inside them. Leha's model says black holes form first, wrapped in a brief, visible cocoon, and galaxies crystallize around the black hole afterward. The little red dots were not a type of galaxy. They were the embryonic phase of supermassive black holes, visible for a cosmic instant, then gone. This would explain UHZ1. A black hole weighing as much as every star in its galaxy would make sense if the black hole came first and the galaxy was still catching up. It would explain the impossible mass ratios. It would explain the mature chemistry, because the cocoon phase would involve intense radiation processing gas at extreme temperatures. And it would explain the vanishing act. Between redshift 5 and the present day, billions of years passed. Plenty of time for galaxies to grow around the seeds, burying the evidence of the cocoon phase beneath layers of ordinary stellar evolution. 341 cocoons, 341 seeds, and if each one became the core of a galaxy, then the supermassive black holes at the centers of galaxies across the observable universe may all trace their origin to a brief, violent phase that nobody knew to look for until JWST pointed its mirror at the deep past. Beyond the Big Bang, the phrase has appeared in headlines since JWST's first anomalies surfaced. It sounds like it means before the Big Bang. It does not. Or at least, it did not used to. What beyond the Big Bang originally meant in the context of JWST was straightforward. The telescope is finding things that the standard Big Bang model cannot produce. Run the clock forward from the initial singularity, through nucleosynthesis, through recombination, through the Dark Ages, through the formation of the first stars, and you cannot arrive at what JWST observes at 290 million years. The physics does not connect point A to point B. The model that starts with the Big Bang and runs forward falls short. In that sense, the observations are beyond what the Big Bang framework can explain, but the data has pushed the conversation somewhere more uncomfortable. JADES&CEERS already contains oxygen at 290 million years. Oxygen requires at least one full stellar generation to form. A massive star must ignite, burn through hydrogen and helium on its main sequence, fuse carbon and oxygen in its core, and explode as a supernova to scatter those elements into the surrounding gas. The fastest massive stars complete this life cycle in roughly 2 to 3 million years. But they need to form first, and before they form, gas must cool and collapse, which requires additional time. The most aggressive models place the first stars at roughly 100 million years after the Big Bang. That leaves 190 million years for a star to form, live, die, enrich its surroundings, and for a new generation to incorporate that enriched material into a detectable galaxy. It is possible, barely. But the nitrogen in GNZ, 11 at 430 million years, is harder. A nitrogen to oxygen ratio, 4 times solar, requires not one but multiple stellar generations, or supermassive stars of 1,000 to 100,000 solar masses that themselves need extreme conditions to form. And the polycyclic aromatic hydrocarbons at 900 million years require sustained chemical processing across generations of asymptotic giant branch stars. Each observation pushes the required starting conditions further back. If the chemical maturity JWST observes demands processes that need hundreds of millions of years to complete, and those processes must have already finished within the first few 100 million years. Then the processes may have started before the epoch we can observe, before recombination, possibly before the Big Bang itself. This used to be philosophy. Roger Penrose proposed conformal cyclic cosmology, in which our Big Bang is merely the latest in an infinite series of cosmic cycles, each one beginning where the previous one ended. Cyclic models from Paul Steinhardt and Neil Turok describe colliding higher dimensional brains that periodically produce Big Bang events. Bouncing cosmologies propose that the universe contracted before expanding, structure from a previous phase carried over into the current one. These frameworks were treated as mathematical curiosities, elegant but untestable. JWST has not proven any of them correct, but it has produced observations that seem to demand conditions prior to the standard starting point. The first few 100 million years were not simple. They were not a blank slate of hydrogen and helium slowly assembling. They were complex from the start, and complexity, at the start, implies conditions that produced it, which implies something came before. The conversation has moved from beyond what our model predicts to beyond what our model's starting point allows. That is a different kind of beyond entirely. Return to the helium-2 absorption line at 1640 angstroms. Because if it is real, it does not just confirm dark stars, it cascades. Dark matter makes up 27% of the total mass-energy content of the universe. It shapes the rotation curves of galaxies, governs the formation of large-scale structure, bends light through gravitational lensing, and leaves its imprint on the cosmic microwave background. Its gravitational effects are measured with extraordinary precision, but dark matter itself has never been directly detected. No particle collider has produced it. No underground detector has registered it. No telescope has observed its interaction with ordinary matter through any force other than gravity. Catherine Freese's dark star model changes that. If dark matter particles annihilate inside primordial gas clouds, the energy released would heat the gas and prevent it from collapsing into a normal star. Instead, the cloud would swell into a supermassive dark star, potentially reaching 1 million solar masses, powered by the annihilation of dark matter particles in its core. The helium-2 absorption line at 1640 angstroms is a predicted signature of this process. Ionizing helium twice requires extreme temperatures that dark matter annihilation naturally produces, but that early stellar populations cannot easily reach. The signal in JADES GS-Z140 is tentative. The signal-to-noise ratio hovers around 2. In physics, that is not a detection, it is a hint, a whisper in the noise that could be real or could be an artifact of the data reduction pipeline. Confirmation requires deeper spectroscopic observation, ideally of multiple candidates, with signal-to-noise ratios above 5. But consider what confirmation would mean. The most distant spectroscopically confirmed object in the universe would not be a galaxy, it would be a single star. The census of the early universe would require fundamental revision. Every bright, compact source at extreme redshift would need to be re-examined as a potential dark star candidate. Some fraction of the impossible galaxy masses might dissolve, because those bright dots are not collections of billions of stars. They are individual objects, producing galaxy-scale luminosity through a mechanism that was not in any model before 2023. Dark stars could also resolve the photon budget crisis. A supermassive dark star would be an extraordinarily powerful source of ionizing ultraviolet radiation. If dark stars were common in the first few 100 million years, they would contribute exactly the missing photons that the reionization budget requires. The unknown source that cleared the cosmic fog earlier than expected might be dark stars, burning through their dark matter fuel and flooding the universe with ultraviolet light before collapsing into the seeds of supermassive black holes. One confirmation could solve three problems simultaneously: the impossible galaxy masses, the photon budget deficit, and the mystery of what preceded supermassive black holes. Dark stars form, shine briefly, exhaust their dark matter fuel, and collapse. The remnant is a massive black hole seed. Wrap that seed in accreting gas, and you have something that looks remarkably like a little red dot. The sequence has not been formally established, but it is suggestive. Dark stars collapse into heavy seed black holes. Heavy seed black holes accrete gas cocoons. Those cocoons eventually shed, and what remains becomes the supermassive black hole at the center of a galaxy, a whisper at 1640 angstroms. It could be noise. It could be the first direct evidence that dark matter does something other than pull. The difference between those two possibilities is about 3 years of telescope time. Catalog what JWST has revealed that nobody knew 3 years ago. We do not know how the first galaxies formed so quickly. Every proposed mechanism, from bursty star formation to top-heavy initial mass functions to modified feedback models, explains part of the observations and fails to account for the rest. The corrected galaxy masses are still too high. The star formation efficiencies are still physically impossible under known physics. The chemical enrichment timelines still require more stellar generations than the available time permits. We do not know how supermassive black holes reach tens of millions of solar masses within 500 million years. The heavy seed model provides a plausible pathway, but it has not been observationally confirmed. No direct collapse black hole has been caught in the act of forming. The model requires pristine, metal-free gas in sufficient quantities, and JWST's own chemical detections suggest metals appeared far earlier than expected, which narrows the window for pristine gas to exist. We do not know what the 341 little red dots are. The black hole star hypothesis is the best available explanation, but it remains a hypothesis. Spectroscopic confirmation of additional objects with anomalous Balmer breaks, combined with X-ray follow-up to detect embedded black holes, could take years. The cliff at redshift 3.55 still matches no template. An entire population of objects appeared and vanished from the cosmos, and the best explanation involves a category of astrophysical object that did not exist in any textbook before 2024. We do not know if dark stars exist. One tentative spectral line in one object at a signal-to-noise ratio of roughly 2 is not evidence. It is a direction to look. Confirmation or refutation depends on deeper observations that JWST can perform, but has not yet scheduled with sufficient depth. We do not know why the Hubble constant has 2 values. JWST confirmed the tension is real and not an instrument artifact. The local measurement and the cosmic microwave background measurement are both precise and both correct within their own frameworks. They disagree by 8% at 5 sigma. Either one measurement contains an unidentified systematic error that has survived 15 years of scrutiny by competing teams, or the model connecting the early universe to the late universe is missing a component. We do not know if dark energy is constant. DESI's measurement at 4.2 sigma is approaching but has not reached the 5 sigma threshold that physics requires for a discovery claim. If dark energy is weakening, the fate of the universe is not what textbooks describe. The expansion might not accelerate forever. It might slow and reverse. But this remains an extrapolation from incomplete data. We do not know what produced the excess ionizing photons that cleared the cosmic fog. We do not know how a protocluster of 66 galaxies with million-degree gas assembled 2 billion years before simulations say it could. We do not know whether the complexity JWST observes at 290 million years implies conditions that existed before the Big Bang. We do not know if the standard model needs patches or replacement. Before JWST, Cosmologists thought they had answers to most of these questions. The answers were clean and internally consistent. The telescope did not provide better answers. It revealed that the questions themselves had been wrong all along. JWST has an expected operational lifespan of 20 years or more. Its fuel reserves, originally projected for 10 years, have been extended by the precision of its launch trajectory. The telescope arrived at L2 with enough station-keeping propellant to operate well into the 2040s. It is not winding down, it is beginning. DESI is still collecting data. Its Year 1 results produced 2.8 sigma evidence for evolving dark energy. By January 2026, that had strengthened to 4.2 sigma. Years 2 and 3 of data remain to be fully analyzed. If the signal holds or strengthens through the complete dataset, the cosmological constant that has anchored Lambda CDM since 1998 will require replacement. On the ground, a new generation of telescopes is approaching first light. The extremely large telescope in Chile's Atacama Desert will carry a primary mirror 39 meters across, 5 times the diameter of any existing optical telescope. Its spectroscopic capabilities will resolve individual stars in distant galaxies that JWST can only image as smudges. The 30-meter telescope and the giant Magellan telescope will add complementary capabilities from different sites and different instrument configurations. Together, these 3 observatories will be able to do what JWST cannot. They will take spectra of the little red dots at resolution high enough to distinguish a compact galaxy from a black hole cocoon from a dark star. They will measure the helium-2 line at 1640 angstroms with signal-to-noise ratios sufficient to confirm or rule out dark matter annihilation as a power source. They will resolve the stellar populations inside red monsters well enough to count the chemical generations and determine whether the enrichment timeline is genuinely impossible or merely implausible. The central question this investigation started with has not been answered. It has gotten worse. Why does the early universe look nothing like our models predicted? 3 years of JWST data have not converged on a solution. They have diverged into deeper uncertainty. Each new observation raises a new variable. Each proposed explanation introduces a new tension. The map of what we know has barely changed. The map of what we do not know has expanded in every direction. Lambda CDM may survive. It has survived challenges before. Dark matter was added when rotation curves did not match. Dark energy was added when the expansion accelerated. The model has absorbed anomalies that would have killed a less flexible framework. It could absorb these too: top-heavy mass functions, modified feedback, early dark energy, heavy seed black holes. Each patch covers a portion of the problem. Perhaps enough patches will hold, or perhaps the patches are the problem. Perhaps a model that requires a new modification for every new observation is no longer a model. Perhaps what JWST has found is the outline of something else entirely, a different history. A universe that was complex and chemically mature from nearly the beginning, for reasons that the current framework cannot accommodate. The next observation could change everything. JWST is scheduled to revisit JADES GSZ140 with deeper spectroscopy in its upcoming cycle. If the helium-2 line strengthens above 5 sigma, the most distant object in the known universe is a single dark star, and dark matter did something nobody believed it could do. If the line vanishes into noise, the search moves to other candidates. Either way, the telescope keeps pointing at the places where our understanding breaks down. It collects photons from an era that refuses to match the story we wrote for it.